Welcome to clickmyproject.com. The title of our product is High Sensitivity CMOS RF to DC Converter in HF RFID band. Next we are going to see the abstract for our product. A fully integrated RF to DC converter operating at the HF RFID working frequency and designed in the CMOS technology is presented in this product. It is based on a Dixon's rectifier, a Pelicon's charge pump driven by a 50 kHz ring oscillator and a voltage monitor. The advantages in integration between passive radio frequency identification technology and sensors have been gaining strong interest thanks to their capabilities of enabling new promising applications. So far, the strongest effort has been dedicated to RFID sensing in UHF band, essentially because of the high read range achievable. The recent huge diffusion of terminals working in the HF band, such as near-field communication readers embedded in most smartphones, makes attractive also the development of HF smart tags embedding sensing capabilities. The main issue in designing similar tags is related to the amount of energy to power up microcontrollers, sensors and other onboard components, as well as to activate the RFID chip. The energy must be harvested from the RFID reader signal. For this purpose, high sensitivity RF to DC converters are needed in order to exploit the very low power levels at the tag input. Besides UHF, also several RF to DC converters at certain MHz frequency is presented. For instance, high efficiency RF to DC converters exhibiting 4 dBm and 1.2 dBm sensitivity respectively. The HF RF to DC rectifier leveraging on a reverse loss reducing technique is also implemented. Next we are going to see the flow diagram for our product. The architecture of the proposed RF to DC converter working in HF RFID band and this circuital model is given here. It is composed of a rectifier, a ring oscillator, a charge pump and a voltage monitor regulating the output voltage between 1.8 volt and 2.4 volt. Moreover, a bi-matching network is adopted to provide an input impedance of 50 ohm. V base peak is the peak voltage of the RF input signal. N is the number of rectifying stages. V base drop is the voltage drop across the Schottky diodes. I base L is the output current of the rectifier to drive the next blocks, and R out RF minus DC is the intrinsic output resistance of the rectifier. The ring oscillator includes also a delay net made with 1 mega ohm resistance RBST and a 6 picofarad capacitance CBST. The delay net is introduced to set the oscillator frequency at 50 kHz for a minus 19 dBm input power level. According to simulations, this frequency produces a good trade-off between oscillator power consumption and maximum achievable output voltage. In order to increase the output voltage while providing an isolation of the output capacitance CBCL from the input RF signal, a two-stage Pelicon's charge pump has been designed to work in cascade to the ring resonator. Indeed, in absence of RF signal, the use of the sole Dixon's rectifier would imply a rapid discharging of CBCL caused by the reverse saturation current of the diodes. On the contrary, in the proposed solution, CBCL is essentially isolated since, in fact, the reverse saturation current of all diodes discharges the capacitance at the output of the rectifier, the standing of the ring oscillator and then the charge pump. Next we are going to see the output for our product. We designed the circuit in the Tanner version 13. Click on the file and give the new design to create a new design. Then on the cell, then click on the new view. So new view is for the creation of the cell. In this cell we can design the circuits. I have created a cell and have designed the CMOS design of the circuit. Then we have to run the process. For that we have to click on the start simulation. Before that we have to set the setup. Give the setup and space simulation and give the path library files path to which we have to add the library file, generic library file. Then click on the transient Fourier analysis for the stop time, maximum time step, print start time, print time step. Click on again and click on OK. This is what you have to do. Then click on the file and give the export and export spice. This is for the export of that cell. Specify the folder in which we have saved the project and give the export. I have already done that. This is for the purpose to create the power file, which is we can see the power consumption of our circuit in that file. For that we have to write certain commands. Entity spice. Click on the run. Our output waveform has created. The out is in milliwatts and in is in nanowatts. Here what we have to add the exported cell to calculate the power consumption. For that we have to click the file open containing folder and click on that cell, exported cell. Then we have to click on the insert command and then click on the output. In that output column there will be power. Click on that and print the voltage source and the start and stop time, which can be in nanoseconds. Then click on again this and click on the output and specify the folder of our design. So then you have to click on the run option. Then the output power consumption report file will be created on that design folder. This is how we have to calculate the power consumption, and we can measure various features also, which is noise and time delay.